Hello, my friends. It's Bradley J. Welcome to the Bradley J. Show, and a welcome return to Doug Arion, my good pal, who's a physicist, astronomer, and professor at Carthage College. We're going to talk about two things. We're going to talk about the asteroid that humankind recently impacted, and the updates on the Webb telescope, because some things happened to it, and we need to find out about the effects of that. So, welcome to the program, sir.
Well, thank you very much. I love chatting with you. Doing it for a long time. This is terrific.
I know. I'm fascinated by this asteroid. That's a big deal to me. I want to find out all about asteroids and about this action that took place. Now, what is an asteroid? What's it made of? I think it looks like in the photo here that you have supplied, it looks like it's made of rocks stuck together by something, which is, I don't know, probably ice. Is that
Well, asteroids
what it
are
is?
all material that was, left over as the solar system got built. So things that came together to make big things made planets, and then there are areas where there are lots of little leftover rocks, and there are tens of thousands, if not hundreds to millions, hundreds of thousands of millions of these rocks floating around in space. Most of them orbit between Mars and Jupiter. They're nowhere near us, but many of them actually orbit near us and come by. And in fact, the Earth has been hit by asteroids. We're hit by little bits, meteorites, all the time. But there's a risk that if one of these things happens to come and smack us, it could do great damage, right? One took out dinosaurs 65 million years ago. A large body exploded over Russia in the early 20th century. These things happen. So this whole experiment was done to find a way to keep that from happening to us in the future.
So, is an asteroid a rock, or is it made up of a bunch of rocks? And
Could be either.
if it's a bunch of rocks, did those rocks come from different places? Like, did the asteroid form, or is it a chunk or chunks of things that formed elsewhere and collected?
Well, guess what? All of the above, depending on the particular body. So there are chunks of rock. There was a big impact long ago on an asteroid called Vesta. These things hit each other. And there are things called vestoids. There are scraps of Vesta that are still floating around. So there are rocks that are parts of it. On the other hand, a lot of these mostly formed, you said, by other rocks coming together early in the solar system. A lot of it was still melted material. And then others that are come together just, gravity pulls on everything. You cannot escape gravity, right? Gravity pulls on everything. So up in space, slowly but surely, these things start to meld together. In fact, the one you're looking at here was clearly a combination of lots of little bits of rock that came together, and gravity is what's holding it together. And that's why this one is particularly fluffy. There's a lot of just small particles and rocks being held together. Then there are other asteroids that are big, really hunks of iron. They're called Stony iron meteorites, big chunks of very dense material. There are numerous different kinds of asteroids, and that makes a difference.
So, jumping ahead a little bit, you must have to know what it's made of before you can calculate the kind of mass and speed of the impact you're going to attempt.
Exactly. And actually, we've done quite a bit of research on that, I and my students. You can take pictures of these asteroids. There's individual dots, with a telescope on the ground, but you can measure their colors. And the way they reflect light is different depending on what they're made out of. Just imagine holding a piece of coal versus a piece of iron. They look different color. So we can actually tell what they're made of from the ground and survey that. And you're absolutely right. You need to know what it's made out of if you know what you're going to do with it. I mean, you wouldn't take a wood saw to a steel plate on Earth. The same thing here. You'd have to use different means depending on what the asteroid's made out of.
Why do you suppose they all most tend to orbit in a particular plane or a particular area?
So when you think about how the solar system forms, you have this, cloud of material that condenses. The core of it becomes the star, the sun, of course, and then the rest of it is, orbiting in this big disk because it's going around quite fast, and so it gets spread out into a disk. And you're going to find heavier stuff nearby and lighter stuff farther out. And there are distances where different things will, what we call freeze out, right? Become solids from that. So in close, we have dense rocky stuff. So you have Mercury, Venus, Earth, Mars, all made of dense rocky stuff. And, Venus and the Earth are areas where water, ice, we have liquid water here. You go out much farther, it's much colder. You have lighter stuff, and you're up with big gassy planets, Jupiter, Saturn, Uranus, and Neptune. In between, you've got kind of never land, right? It's not enough rocky stuff to make rocky, big rocky things, and it's not far enough out for stuff to be cold enough to freeze into these big gassy things. So you end up with this sort of scrap, right? It doesn't quite make one or the other, and that's the area between Mars and Jupiter, right? Everything inside of Mars is one thing, Jupiter's the other, and you have this never land. So we end up with asteroids there, stuff that could kind of sort of come together, but couldn't form big planets, couldn't form big rocky planets. And so you have this band out there. It's pretty cool. You can actually understand all this stuff. It's really neat.
So an asteroid is formed kind of from local material, local meaning within the diameter of our solar system. It's not from other solar systems that show up here. It's made out of the same stuff our solar system is made of.
That's what all of these are made of. Now, there are asteroids, rocks that have come from other places. We had Umeomea, if you remember, a couple of years ago, came by. That was a rock that came from some other solar system and came flinging in our direction. So
I see.
It's possible, but all the ones we're caring about here, this is all stuff that's in our solar system and was made along with us. Yeah.
So when one comes from another solar system, did it get knocked out of the orbit of that solar system, or is its orbit so big that it includes our solar system?
No, it got knocked out.
Oh, wow. So there was some big collision somewhere, and that was a fragment, probably.
Well, we've had lots of things like that. So when any two bodies get near each other, one's going to get sped up and one's going to get flung out, if it's a small thing and a big thing. The same way that we've used planets to send satellites out, right? The Voyager spacecraft have left. They went by Jupiter, picked up a lot of speed and flung out and will never come back. We have rocks will do the same thing, right? A rock passes nearby something and gets flung out and it's not coming back. It's going to float out there and maybe it reaches something, maybe it doesn't.
Okay, what was the name of this particular asteroid again?
This one's called Dimorphos.
I like that name. And
cool name.
It was as big, they say it was as big as the Great Pyramid?
About that big, yeah, right. So it's actually not a very big rock as the rocks go out there. I mean, the one that took out the dinosaurs was between 6 and 10 miles across. This thing was, many hundred meters across. But it was a great way to test if we smack something into it, will it change its direction? So, you could model this thing out, do it, and it worked way better than predicted. It was very successful, completely changed its orbit.
So did it work way better than expected because of its unexpected fluffiness and
yes, that
lack
had a
of
lot
mass?
to do with it. Yep.
Okay.
Exactly.
Fluffiness meaning it was kind of crumbly and not a chunk of iron.
Right.
Okay.
Right. It's like biting into a hard cookie versus a soft cookie, right? You bite into a hard cookie and little bits of cookie come off.
Okay. How much notice do we get usually in order to cook up some scheme to divert the course? How much time?
Well, that's an interesting problem because it depends on how far away it is. So here are the trade-offs, and it makes it a hard problem. It's easier to deflect something and have it miss if it's far away, right? You don't have to do it much. In fact, I'm looking out here over the golf course at the Mount Washington. It's very hard to hit a hole in one off the tee because, the hole is really far away. When you're really close and you're putting, you expect to get it in the hole. The thing is, the farther away it is, the harder it is to know with precision that it's actually going to hit us because you don't want to put all that effort in if it's going to miss us anyway. It's very expensive and very hard to do. So there's sort of an intermediate where it's close enough that you're really sure it's going to hit, but far enough away that you've got time to work with it.
Well, how far? What is that sweet spot?
Exactly. So the bigger the telescope we can use to find these things and get precision about their orbits, the farther out they'll be when we know it's going to hit us and the more time we've got to fix the problem. So that's why some of these big telescopes are being built to find those rocks, to know for sure, rather than gambling that, oh man, maybe this. Oops, it hit. That would be bad.
So that must be one reason it's important to have big telescopes in space rather than on Earth, because there's so much light on Earth and so much space junk that you can't see the asteroids.
Actually, the telescope that's being built for this problem in particular is called LSST. It's in the Vera Rubin Observatory, and it's actually in Chile. It's a ground-based telescope that's very big, but it's devoted to this kind of problem. It's going to scan the entire sky every 3 nights and find things that move or change. And then when you find something, yes, you're right. Then we use the big space telescopes to get the details so that we know what's really happening with them.
And all these satellites we're throwing up there make it more difficult to notice these asteroids, correct?
Exactly. That's a big problem. This telescope that's going to be looking up, it's going to be very hard to take images without those streaks going through them. And that could hide the rock that we're looking for. It's a problem.
Okay. They all go pretty much the same speed, or are they wildly different in their speeds?
They're different in their speeds because it depends on the way the orbit is oriented, right? If it's starting to fall in towards the sun, right, one that's going to come towards us, it's going to pick up speed as it comes in. Ones that are in a nice orbit going, sideways out there, just going round and round, they won't look like they're moving as fast. So, yeah, we have to keep track of all of them.
We're with Doug Arion, physicist, astronomer, and a professor at Carthage College, talking at this point about asteroids. It must be pretty... Oh, let me change the question. Do they have to know the speed of it exactly and fire their gun and hope that the calculations are right? Or can they get it generally and then make adjustments as they get closer?
It depends on the method that you're deflecting it with, but generally, obviously, the more accurately you know it, the more efficiently you can reach it. So yeah, you want to know it as accurately as you can, but yes, the spacecraft can adjust its trajectory as it's heading there.
It must be difficult to calculate a speed exactly because you don't really know how big it is. How do they do that? How do they calculate the speed? You can't just do redshift kind of things.
Actually, you do.
You can't just do light analysis. So how do they figure out how fast it's going?
Actually, you use those techniques. So you take, you're not going to know from one picture. You take a whole series of pictures, and each picture, the thing's in a different position. So you can measure how fast it's moving this way by doing that. The distance, the speed forward and back, yeah, you use redshift and blueshift with very, very precise instruments to get that component of it. And you put those together, and you can determine the orbit. Now, how big it is? Well, you can, from the light that comes off of it, you can figure out what kind of rock it is. And from what kind of rock, you know how reflective it is. And if you know how bright it appears, you can figure out how big it is, because that tells you how much light is coming to you. So even, believe it or not, even the individual pinpoints, we can tell you roughly how big they are, which is pretty cool.
Kind of a side question. Do you have to know what it's made of first so you can, because that affects what, right, the spectrum of light that comes off it. And do you need to know that the material of it first so you can know does that affect the material affect the redshift and blueshift, which affects the calculation of speed?
Right, exactly. So when you measure the spectrum, you then know what it's made out of. You then know how much light is reflecting, and then you can figure out all those other pieces. Exactly.
That's pretty complicated to me. Let's see. So we don't know. So the amount of notice we have is different each time. And can you give me a rough idea of how they, once they figure out the speed, how they make the craft that they shoot up there hit it? How does that work? I mean, that's basic docking maneuver in space, but still, how does it work? How do they calculate that?
Pretty much the same way, in that where this object is, where it's going to be, right? Once you have the orbit figure, you know where it's going to be. And you develop with your rocket the guidance system that says, okay, this is how long it's going to take to get there. This is where it's going. It's exactly the same thing that a quarterback and a receiver go through. When you throw the ball, you have an idea of where the guy is going to be when the ball gets there. Of course, some quarterbacks are better at it than others. But with this process, we've been very successful with docking things going back to the 60s. Believe it or not, it's not something you do on the back of an envelope, but it's straightforward calculable now. There are nice models you can run to do it.
Do people calculate it, or are the computers they feed it in and it's much easier? Computers do it.
Oh, computer. To get the precision you want, computers are doing it, and you include all sorts of effects. So, everything's pulling on everything. So you can get incredible accuracy now by including the effects of all the little things that are going to drag on this spacecraft until it hits exactly where you want it to hit.
Okay, these things are very far out, and so you can move them just a little bit and make it miss Earth. Like Earth is 8,000 miles across, 25,000 miles around. So say it was headed dead center for Earth, that would be a radius of 4,000. See, if it was headed for dead center of Earth, how much? I mean, can you move it 1 inch and have it move 4,000? Miss Earth by just moving it 1 inch? Is that the kind of numbers we're talking about?
It's not inches, but if you caught it far enough away, the farther away it is, the less you have to move it so that it eventually bypasses us, right? So the farther away it is, the easier it is to give it a push. The biggest thing you're actually changing isn't so much where it is, but the direction that it's moving, right? So for example, if you were a player playing golf with somebody, you don't have to make them move where the ball is on the tee. You need to make them kind of change the angle of their club just a little bit, right? You sneeze just as they swing. And when the club hits at a slightly different angle, it's going in a different direction. And that's what we're doing here. We're changing the angle. So it's traveling this way. We change the angle just a little bit.
That is amazing stuff. So you say it was more successful than expected. Give me can you quantify that for me? Like
sure.
How much more they expected X and they got X plus what?
They got almost 10 times as much of an effect as they were looking for. So
wow.
This particular asteroid actually is a little bit that goes around another asteroid. And so what you could do is, you know how long it's been taking that asteroid to go around once. Now you whack it, you expect that orbit to change. And so the length of time it goes around is going to change by a bit.
Oh, wow.
And that's easy to calculate. So it was a nice thing. It's like we can test the system out and we can directly measure what the effect, because if you're just deflecting something that's coming towards us and it's far away, it's going to take a long time to know. With this, you could know right away. It was known within hours how it worked. And they were expecting the orbit to change by, X number of minutes. It actually changed by almost 10 times as much. So that was a big part of the fact that this thing was a fluffy object, right? So you hit it, a lot of stuff comes flying out. That helps you, right? That helps you move it.
Right.
And the orbit changed tremendously. So that's really good news. Really good news.
So I understand the object that hit it was the size of a refrigerator. Did they pack it with heavy stuff so it has more mass to move the thing more? Like, is it a refrigerator filled with iron or something?
Yeah, it was a relatively heavy spacecraft. And again, that's one of those trade-offs. If you said, okay, we want to do this, but the asteroid's really far, it's big and it's really far away, you have to launch something that's heavy, right? The heavier thing you launch, the bigger the rocket you need. Mm-hmm. But the other thing you can do is make it go very fast, because it's the combination of speed and weight that makes the difference, right? So that's where a lot of smart engineers have to do their work to say, okay, what's this combination, right? What would the fuel requirement be? How big a rocket do we need? to get enough oomph on this particular thing to move it the amount we think we need to move it. And it's not terribly hard physics, but it's physics, right? We work those problems.
It is
to be able to do that.
I gotta say that's, people wonder, why should we be in space, and they don't see any real world benefit. Well, in this case, you definitely see a real world benefit. It's pretty cool.
And for sure,
it is pretty amazing. But as you say, it's kind of straightforward. The calculations are not amazing. It's just executing them properly. I mean, there's a lot of places you could make a mistake down the road, and if you miss, you're kind of out of luck. Do they build more than one in case you missed? If they were a real threat, they probably launch more than one in case the first one missed. Would they have a redundancy?
I mean, those are policy questions. I mean, this was the first real experiment to demonstrate that you could do this. I mean, I think everybody involved would be pretty darn sure that you could do this, but you never know until you try, right? I mean, you got to hit it at the right angle. It's got to be the right speed. You got to do all that stuff. And it worked beautifully. So now you try, more complicated experiments. But, we don't have a fielded system to do this. It's not like, oh, okay, there's a whole bunch of rockets in the ground ready to go in case something happens. This is a first experiment towards ultimately having that capability. Now, what would you do? What would you actually field? That's a good political science question, right? What's the investment going to be? How many countries would be involved? How many would you put up? How ready does it have to be to fly?
Yeah, how ready? I'm curious about that. Yeah.
Right. Yeah. I mean, if you find these things when they're far enough away and you say, we have 6 months before we have to launch something, then you don't have to have it built to start with. But if you have something that's like, okay, our window is a week. Well, you can't build one of these things in a week.
No.
So you have to have them ready to go in a week, right?
Yep. That's difficult because you don't know what size of rocket, how fast it has to go, or how heavy the payload has to be until you find the asteroid. So you kind of maybe have to have like the skeleton's all set up. So, we're going to need this much fuel. Okay, put that in there. And you can have a series of different sizes of projectiles or crafts that hit it of different weights. I don't know. Let's move to the Webb telescope. So last we spoke, wildly successful. First question about that was how successful was the setup? Like hundreds of things had to unfold and happen for it to work correctly. How many of those worked correctly?
Absolutely every single one worked perfectly. It's mind-boggling, absolutely mind-boggling. But all of these things that had to unfurl in just the right order, lock in place in just the right place, and it all worked beautifully. I think all the engineers who worked on that, I'm sure they had lots of sleepless nights while it was happening, and then woke up one day and went, okay, it's all there. Wow, that's very exciting.
And now the images it gets, how do they compare to expectations?
As good, or in a lot of cases, even better. The telescope is functioning so perfectly, it's fantastic. Absolutely.
How do you use those images? Instead, it's not just ooh and ah. What can we figure out as a result of the clarity of the images?
So, for example, and the first image I put up here, I don't know if you can switch over to it, is one of the first images that it took. And
I only see the asteroid.
You see the asteroid. I told it to stop sharing that and to start sharing a different screen. Why did it do that? Let's see if I stop that.
Okay, you did stop that. Yep.
Okay, now I'm going to share screen, and I'm going to share. No, where'd that go? Oh, here we go. This screen.
Yeah, here it comes. Very good.
There we go. Okay, wonderful. So one of the things that this telescope can do, and you have to remember that everything you're seeing in these pictures is invisible to our eyes, not just because it's faint, but because it's in the infrared. It's light that our eyes aren't sensitive to. So even if your eyes were just incredibly super sensitive, you still couldn't see this, right? This is invisible light. It's infrared light. And we need that because in this picture, for example, we're looking at things, all those little streaks, not the bright blue things, but the things in the background there is actual light from galaxies, from stars that were formed so long ago that the universe has, as it expanded, stretched that light so much that it's now in the infrared. So it was visible light when it was emitted, it's now infrared. So no other telescope was able to see this before, right? Hubble can't see into the infrared. So we've never seen that. And this means we're actually seeing stars and galaxies really, really early in the formation of the universe. In fact, one of the great discoveries already is that there were galaxies forming much earlier than we thought they could. You know, we thought early on there wouldn't be enough stuff quite congealing to become galaxies, but it looks like, you know, within a few 100,000 years after the Big Bang, this stuff started coming together to make galaxies. And that's really amazing. And you couldn't have done that any other way because, again, that light's been so stretched, we can't see it any other way.
So if the telescope only sees infrared light, that means that the images are infrared light, and how can we see the images of infrared light if we can't see infrared light? Does the computer have to assign visible spectrum colors to this stuff?
That's exactly what it does. So, for example, even when you take a picture with your digital camera, or right now, these cameras that are showing images of us on this show that we're doing together, you know, the camera just creates data. Every little site in the picture just is a collection of numbers, right? And then your screen converts those numbers into brightness and color.
Okay.
So that's exactly what's done here. The camera produces numbers in every single little spot on there. And the number is how much energy I collected at each of these wavelengths. And then the computer converts that into colors we can see. And so the longer the light is, the redder we make it look. The shorter it is, the bluer we make it look, even though all of that is still light that we can't see with our eyes.
Okay. And there was some damage from some little space bullets, some particular matter. What was it? What was the stuff that hit it? What is the actual stuff? Space particles made out of what? From where?
They're actually little bits of rock. They're micrometeorites. So very similar micrometeors, meteorite to the ground, micrometeor. So just remember, we're talking about asteroids. We'll say, okay, there are these big rocks floating around. There are itty bitty rocks floating around, things that are tiny specks, little specks of things, you know, things that are literally like grains of sand, all the way up to things that are the size of marbles and then, you know, bigger. And obviously the smaller ones are more common. So one of these little grains of sand moving at, by the way, over 20,000 miles an hour. Because remember, these things are up in space moving very fast. Smashed into one of the mirror segments on the telescope. It did
How big was that?
Little bit of local damage, which really doesn't affect the telescope a lot, but it was enough to actually knock the mirror out of alignment. So that mirror had to be realigned.
Wow.
But, you know, there's stuff out there. Stuff happens. I mean, it's not very different. You have a telescope on the ground and you get a gust of wind up there. There is stuff floating around, and it will ultimately be, you know, over the very long term, the demise of the telescope. Everything we have up there is eventually damaged, but hopefully it'll last a long time without any significant problem.
Is there a little motor on each one of the panels that can be operated from Earth? And luckily, the damage was not serious enough to damage the motor.
Well, that's correct, right? It was just I mean, all things considered, a little impact, but it was, remember, the precision of these mirrors is so high that any slight change in tilt of it ruins the optic. And yes, the whole things were aligned in the first place by a series of motors on the back of each of those segments. Each of those hexagons has a bunch of motors behind it to align it. And so that had to be realigned, and that gets done from the ground.
So much has to go into this, like getting a motor to function in space. Like there's all kinds of stuff, unknown variables out there that might affect the operation of a little motor. Like, I don't know, lubrication might act differently, or is it an electric motor? Electricity might work differently. It is crazy Crazy amazing. Let's see.
Oh,
By the way, how big was that particle? Like a sand size
yeah,
or okay.
yeah, like a large sand particle. Yep,
So that must
absolutely.
be kind of a worry for astronauts doing spacewalks because
Oh, absolutely.
one of these
Um,
things could go right through them.
Yeah, I mean, you have to be careful with those things. You do have materials there that can absorb, significant impact. The space station itself has had holes in it that have had to be patched from things like this,
Wow.
small impacts, which will punch a little hole, and it's like, okay, we have a little leak, we're going to go patch the leak.
So
They
these
do.
spacesuits are kind of bulletproof. They try to make them. They make them out of Kevlar or something. Partly, is there a layer of something that is bulletproof or teeny meteor proof?
I don't know what the material compositions are now, but yes, I mean, you want something that's very abrasion proof anyway, because you wouldn't, you're working outside. You wouldn't like. I'm sure you've worked on something where you go, oh darn, I just tore my T-shirt, right?
Yeah.
Ripped it against the ladder.
Yeah.
That would be bad in a spacesuit. So a lot of it is very abrasion resistant. So I would think that would help a lot.
When they build these things, do they try to have no sharp corners that astronauts could tear their suit on? Do they think that thoroughly?
I'm sure those things are a major concern. If
Wow.
you look, especially at places where they're going to be moving and doing things. Yeah, there's a lot of stuff to consider if you're going up in space and you can't fix things easily.
So they already working on a big new, and the new version of the Webb. There was Hubble, there was Webb. Is the next generation of out in space telescope being built, and how is it? If so, how is that different?
There really is no next space telescope planned at the moment. I think that's there are so many aspects of space science that are being looked at now. That's kind of a next priority. It's like, okay, what's the next thing that we would want to be working on? And I don't think that's been decided yet. There are even debates now as to which spacecraft to send out to other planets. There's a definite wish to go to visit Europa, for example, which is covered with ice and has all sorts of cool, interesting, gooey things on it. It'd be like, that would be a really cool place to go. But they're a big, it's a big competition for funding. Going back to Venus. We haven't had anything on Venus in a very long time. A lot of things to explore. So,
okay. One final question: what has anything happened recently in the world of physics to upset the apple cart, to change things in one direction or the other, in Einstein's direction or the Copenhagen direction? What's happened recently?
I don't know that there's any major recent thing going on there, but lots of folks are continuing to work on that. One of the things that might be of note, the Nobel Prize in Physics was awarded last week, and it was awarded for the work that went into showing that particles can be primarily in one direction versus another direction, and that ends up feeding into parts of the theory as to why we have more matter than antimatter, right? Why didn't we get equal amounts of matter and antimatter? So there's work going on all the time to get into these really, really big questions. And
Okay.
I know the ones you and I talk about a lot because they're very interesting.
I'm interested in two things: disproving the Big Bang, because as you know, I have problems with it. It's just too arbitrary. How could it happen just one time? Nothing happens forever, and then pow, something happens out of the blue, and only happens once. That doesn't seem right. And the whole multiple dimension thing is really interesting to me. So any new progress on either of those is interesting to me. Doug, thank you so much. I know you're coming to us from the ski center at Bretton Woods, right next to the Mount Washington Hotel. There's no snow up there yet, right? Yep. No snow yet, right?
No, yet, but we will have snow. All your folks, if you want to learn to cross country ski, this is a great place to come up and try it. And a reminder to everybody also, separately, remember to check out my program site, mountainsofstars.org. Lots of resources, places to learn lots and lots more about all these topics that Bradley and I talk about all the time. So it's mountainsofstars.org. Please check it out.
Right, and you could actually meet you. One could actually meet you. You are an instructor of the cross country skiing, correct?
Yes, I am. That's one of the very fun things we get to do in the way here. I'd love to take you out and teach you how to ski.
It would be a double whammy if you were interested in the stuff we're talking about, because while you're getting a lesson in cross country skiing, you could probably talk to Doug about astrophysics and stuff. So as always, thank you so much. This might have been the best one ever. I love it. They just keep getting better and better. Folks, share this with folks you think might enjoy it. I'll do it. Doug shares it as well. So I can't wait to see you and do this again soon.
Sounds great. Looking forward to it.
Bye bye. We'll be
Bye now.